course. In the earlier classes, we have talked about what is phase and what are different types of phases and how to distinguish one phase from another, what is components. And also we have talked about lot of thermodynamic functions, how to represent them in form of plots. Also, we have seen the free energy versus temperature curve. Also, we have seen how free energy depends upon temperature, compositions, right? And also, we have seen a lot of plots related to free energy per mole versus composition, right? And how to draw it. And also, we have seen how to show delta H mix in form of plot in a free energy versus composition curve, how to show this delta S configuration or delta S mixing, how to show minus T delta S mixing, right? A lot of things. Also, we have derived expressions for this free energy for a ideal solution, free energy for a regular solution. So a lot of things we have discussed up to lecture 8. Fine. So in the lecture 9 and 10, basically, we'll see the significance of the tangent drawn to the plots. When we draw a tangent to free energy curve, what will happen? What is the significance of that? And also we'll see some phase diagram, like isomorphous phase diagram and eutectic phase diagram, and how this phase diagram will be converted into this free energy versus composition diagram on the basis of different temperature. So that is our main motive, because you understand phase diagram means it is a plot between temperature versus composition, right? In y-axis we have temperature axis, and in x-axis we have composition axis, right, in the phase diagram. And that phase diagram, that means, you understand, phase diagram means lot of phases will be present, right? If it is an heterogeneous system, then lot of phases may be present, and these phases have a particular stability at particular temperature. So if we choose different temperature, we can draw different free energy versus composition diagram out of that. That is our main topic. You should know how to draw a free energy per mole versus composition diagram out of the phase diagram at different temperature, because different phase have different stability at different temperature and at different composition. Okay, that is our main topic. Okay, so these are the today's content. The phase stability in heterogeneous system. So what is heterogeneous system? Obviously the system which have more than one phase. The best example I can give you, like eutectic system of lead and tin, right? Like isomorphous system of nickel and copper, right? Or like iron carbon phase diagram, where a lot of phases are there, right? So if a system is having more than one phase, that kind of system is called heterogeneous system. So we'll see the phase stability. As I told, if lot of phases will be there, or if more than one number of phases will be present in a system, then they will have a stability. They are stable at a particular composition at a particular temperature range, right? It doesn't mean a phase will always remain stable throughout all the composition, throughout all the temperature. It is not so, right? Some phase will be stable at low temperature, some phase may be stable at intermediate temperature, some phase may be stable at higher temperature. Similarly, some phase may be stable at a certain composition. If you change the composition, that phase will be not there. It will transform. So phase stability will tell you about the phase transformation, that a particular phase is not stable at a particular definite temperature and composition. So if you change the composition, if you change the temperature, new phase will come out, right? So that is phase transformation. Okay, so you can see this is a again free energy per mole versus composition diagram, right? We have pure component A here, we have pure component B, and we have drawn free energy per mole versus composition curve for two phases or two solid solution. One is alpha, one is beta, right? So you can see this is the free energy per mole versus composition curve for alpha phase or alpha solid solution phase, and this is the free energy per mole versus composition curve for beta phase or beta solid solution phase. Okay, and what is interesting here, we have taken a temperature of T is equal to T1. Okay, And you understand this is xb means the composition axis. Composition of B from this end to this end, right? Because this is 100% A, this is 100% B. Okay. So from this diagram, we can say, for example, this A is FCC crystal structure, B is BCC crystal structure. That means A is a metal having FCC crystal structure, B is having a metal having BCC crystal structure, right? And we understand, suppose alpha phase or alpha solid solution means what? Alpha solid solution means B in A. Okay. Similarly, beta solid solution here means A in B, right? So there may be some solubility limit, right? That means B is soluble in A is soluble in B is soluble in A, and A is soluble in B, but there is a solubility limit to that. Fine. Anyways, so you can see this alpha phase curve is intersecting the beta phase curve, right, at this point. So what exactly it means? Can you tell me? If this is the intersection point of alpha phase and beta phase free energy versus composition curve, at this point, what is happening? What is common?
Composition of A equal to composition of B.
Okay, that's fine. Very good. Composition is same composition, for example. Anyways, at 50-50, if you are saying at 50-50, so suppose the composition is same. Okay, anyways. Anything else you can see? They have what?
Same free energy.
Free
Same
energy.
free
Very good. They
energy.
have same free energy. Excellent. So the first one, what Asirbat told, if this intersection will be here at this point, can you say they have same composition of A and B? No, I cannot say. You understood my point? If intersection will be happening at this end, can you say that composition of A is and composition B are same in this both phase? Answer is no. You understand my point? But what is same? The thing is the free energy of both alpha phase and beta phase are same where it is getting intersected, right? So at the intersection of this alpha phase and beta phase, the free energy are same. So free energy are same means both will be stable. You can say in a normal sense, you can say alpha is stable and beta phase is stable at the intersection point. That means at that particular composition, free energy of alpha and beta phase are same. So both will be stable, both will be existing over there. You can just simply say, right? But there is an interesting thing here. Just have a note. Suppose this is the free energy. This is the free energy of alpha, which is also the free energy of beta. Both are same. And this is the composition, for example. This is the composition, right? So you have to remember, whenever this kind of situation arises, the composition will not remain same. The composition will change, right? The composition will change in such a way that the free energy will be minimum and minimum and minimum. It will go down actually, right? So that means initially the free energy is suppose this much, and due to change in composition, the free energy will decrease again. Where it will come? The alpha will come to this end, beta will come to this composition. Just have a look. I'll show you the diagram here. So this is the intersection point. See, this is the alpha free energy curve. This is the beta free energy curve versus composition curve, right? So this is the intersection point. At this point, free energy of alpha and beta are same. Both will exist, right? Both have same free energy. Both are stable. But this composition will not remain now. The composition will reduce, or the composition will change actually. Why composition will change? Because the system want to decrease its free energy. The system free energy will not remain because the initial free energy is this much, for example. This free energy will not remain. The system want to reduce its free energy. How system can reduce its free energy? By changing the composition. How it can be changed? You can see first the composition will become this much and this much, right? You can join these two lines. So this is the composition of alpha. and this is the composition of beta. So if the composition will change, you can see there is a change in free energy. So initially free energy is this much. Due to formation of this kind of composition, now the free energy is reduced. Further, it will reduce to the minimum free energy point. Where is the minimum free energy point? This is the minimum free energy point of alpha, and this is the minimum free energy of the beta phase. So this is the composition of alpha, and this is the composition of beta. You can join them. You can draw a tangent, right? So how to do that? Just simply draw a tangent to these two curves. Obviously the tangent will intersect the minimum point of alpha and minimum point of beta, right? So this where this tangent will intersect these two curve at the minimum point, that point is the composition of alpha and composition of beta, right? So initial composition will not remain same. It will change to this composition and this composition, and this is the tangent. You can see this image. The tangent is drawn to this two curve, and it has intersected the lowest point of alpha and lowest point of beta, which shows the minimum free energy. And you can write, so initially this is Z and this is the final G, this point. So this will be delta G, obviously, right? And what is this composition? If this is XB, so you can see the composition of this point is XB alpha, and this composition is XB beta, right? So this composition will not remain same. It will be transforming into new composition. This is the new composition of alpha. This is the new composition of beta. Why this composition change is there? Because they want to reduce the free energy, right? They want to acquire the stability. Okay. I think up to this you people have understood.
Yes, sir.
So you have to remember, whenever there are two or more number of free energy versus composition curves, and they are intersecting at a point, that means both have same free energy, and that composition will not remain. The composition will change because the system will want to reduce its free energy. And where the composition will change? The composition change can be determined by drawing a tangent to the two curve or three curves if present, right? Obviously the tangent will intersect the lowest point of the particular curve, right? And that is the composition, actually, new composition. And that change in free energy is delta G, because initially free energy is this much, final free energy is this much, so this is delta Z, right? So anything else can be determined? Yes, a new thing can be determined. Just have a look, which can be shown in this image. Can anybody figure it out? Suppose this composition is fixed or different. Tell me, this composition or same, these are all same curve, right? This composition and this composition is fixed or different for alpha and beta. It is fixed. This composition is fixed now, one single point, right? One single intersection is happening at one single point. So this composition is fixed for alpha phase and beta phase, right? But as I told, this composition will not remain. It will transform into new compositions because it wants to reduce its free energy, right? So if this is the situation, then you can simply say, just have a look. Again, this is free energy versus composition axis, pure A, pure B, right? And this is the curve of alpha solid solution. This is the curve of beta solid solution, and they are intersected at this point. So free energy has reduced to this much. By drawing a tangent, you can see, when you draw a tangent, this tangent to these two curve intersected at the lowest point of alpha and lowest point of beta. So this is the new composition of alpha, this is the new composition of beta. So a new thing can be determined. What is that new thing? The new thing is range of stability is there for alpha and beta. That means alpha and beta phase here do not have a fixed composition, or it is not stable at a particular composition. It is stable at a range of composition. Alpha and beta will remain at a range of composition. The stability of alpha and beta will be in a range. It is not fixed. But if this is a single composition, then it is fixed. But now composition is from here to here. Just have a look. So that means how you can determine the range of composition of these phases? Just after drawing the tangent, this is the tangent drawn this to the two curves, alpha and beta. So you have to draw projection. So this is the intersection part. You draw a projection to the composition axis. So here this is the intersection of this tangent to this curve. You draw a projection to this composition axis. So now you can see the range of stability. So alpha phase will be stable from this pure A to this much of composition. And similarly, beta phase stability is from pure B and to this much. And what about alpha plus beta range stability? It is from this point to this point. You people got my answer? What I mean to say?
Yes, sir.
Yes, sir.
Okay, let me repeat. If you have any confusion, let me repeat. So you have seen, you have two phases in this free energy versus composition axis. One phase is alpha phase, one phase is beta phase. Or you can say alpha solid solution, beta solid solution. And they are intersecting at a point. But the point where they intersect, that is the free energy of both. And free energy of both are same now for both phases. So both are stable, right? Both phases will remain, right? But that composition will not remain. The composition will change for alpha and for beta. So how to find out the change in composition? Just by drawing a tangent to the two curve. And that tangent will intersect what? The tangent will intersect the lowest point of the two curves. Where they intersect, that become the new composition. So initial fixed composition will changing from new composition, which is this one and this one here, right? Initial composition is this one, but new composition is this one for alpha, this one for beta, right? This is a tangent drawn, right? So you can draw a projection. You can see the composition here is xb alpha, here xb beta, right? So I mean to say is, after doing this, you can also see that alpha phase, beta phase have a range of stability now, or alpha plus beta phase have a range of stability. They are not stable at a definite composition. They are stable at a range of composition, right? So if you start from this pure end A, that means this is pure, means 100% A is there. So alpha is stable from this pure 100% A to composition of xb alpha. This is the range of stability of alpha. So you maintain any composition, alpha will be stable, right? In between this. Similarly, the stability of beta will start from 100% B to xb beta up to this much of composition. So beta phase will be stable at the around this composition. It is not like you will say beta phase will stable up to this. No, it is stable up to this point. And what about alpha plus beta? Alpha plus beta will be stable from this point to this point. Okay, which I've shown here. Just see what I've done. Range of stability of alpha phase, this reason. This is the range of stability of beta phase, and this is the range of stability of alpha plus beta. You people understood my point now?
Yes, sir.
So tangent to the curve is very important. You have to remember, right? So whenever you have two phases, three phases, four phases, you draw tangent, and it should touch the lowest minimum point, and you can tell lot of things. If you remember any other things I have told earlier, if you extend this tangent to this pure end and to this pure end, what it will tell? Can you tell me? The tangent drawn to this pure end will show what?
Composition of
Chemical
A.
potential.
Chemical potential. But we have two phases. So what it will tell? It will tell this is pure end A. That means chemical potential of A in alpha phase will be equal to chemical potential of A in beta phase. You understood my point now?
Yes, sir.
Similarly, this end will tell you what? This end will tell you chemical potential of B, because this is B point. So chemical potential of B in alpha phase will be equal to chemical potential of B in beta phase, right? But if there will be a single phase, then you have to tell this is chemical potential of A, and this end will be chemical potential of B. But we have two phases. So that's why you have to tell about the chemical potential equality. Okay, up to this it is fine. Then everybody remember the isomorphous phase diagram. Anybody tell me? Can you tell me what is interesting about isomorphous phase diagram? What it means actually?
100% solubility.
100% solubility in what? In both in liquid state as well as in the solid state.
A solid state.
Very good. So that means you can take two components. For example, you can take copper and nickel. You mix them. the copper and nickel will be 100% soluble in liquid phase, as well as it will soluble in solid state also. So there is 100% solid solubility in liquid and solid state, right? Okay. And any other example, anybody remember? Any isomorphous phase system? Gold and silver. That's why silver is added to the gold, sometimes, to make it 22 karat or maybe 20 karat. It depends how much amount of silver is present in gold. So silver, gold are also isomorphous phase system, right? Copper in gold also sometimes. Anyways, because they have same crystal structure and size difference is also nearly same. You remember the Hume-Rothery rule. Everybody remember the Hume-Rothery rule? Fine. The structure factor, size factor, valency factor, and electronegativity factor, right? These are the 4 factors which decide the solubility limit in a substitutional solid solution. You people remember this or not?
Yes, sir.
Okay, fine. So, okay, so this is a phase diagram you people remember. Okay, can you tell me, so phase diagram you people remember. In a phase diagram, y-axis will be temperature axis in degrees centigrade always, and the x-axis will be tell you about the composition, right? So this is pure and A, this is pure and B. That means this is 100% A, 0% B. This is 100% B, 0% A, right? And this is the composition XB. We are changing the composition of B in this direction, right? So anybody remember what is this point? This point will show what? And this point will show you what?
Melting point of pure
Very
A
good.
or melting
Very
point
good.
of pure B?
This is the melting point of pure A. This is the melting point of pure B. And anybody remember what is this boundary called? Top boundary is called what? And bottom boundary is called what?
Solidus boundary and liquidus.
Which one is solidus?
Above.
Bottom one is solidus. You just remember, don't be confused.
Sorry, sir.
Bottom one is solidus line or solidus boundary, and top one is liquidus. The simple way I told you, liquidus boundary means it will separate liquid and two phase. Solidus boundary means it will separate solid and two phase, right? Or you can simply say liquidus line is that line above which everything is liquid, right? And solidus line is that line below which everything is solid. This is a simple way I told you in Introduction to Physical Metallurgy, I remember, right? Anyways, so you understood. So this is the melting point of pure A, that is TMA, and this is the melting point of pure B, TMB. So here what I have done, here in this phase diagram, I have chosen 5 temperature. Just carefully look at the 5 temperature positions. So this is the T1 temperature. You can see this is the T1, top temperature is T1. Just below that, I have TMB. TMB is the melting point of B. So I have chosen this temperature, TMB, which is touching this end point only. This one. Then I have chosen T2 temperature. T2 temperature is intersecting the two phase region. This is a single phase, then two phase, then single phase again. Okay, this is T2. Then and the temperature is TMA. That is the melting point of pure A, right? So this is the temperature which is intersecting this point, melting point of pure A, right? And the temperature is T3, which is in this region, alpha region only. Okay, so these are the 5 temperature I have chosen. So can you tell me how many phases I have here? How many phases I have in this phase diagram? 2 phases, basically liquid and alpha, and one is the mixture of phase. Okay, one is the phase liquid phase, one is alpha phase and the phase, one is mixture of phase liquid and alpha. Okay. Okay, so now this 5 temperature is chosen. So now you can see, as I told, now this is a very interesting part. You have a phase diagram, which is temperature versus composition diagram, right? And you have chosen 5 temperature. So for each temperature, you will be having a free energy versus composition diagram, right? G versus X diagram, or free energy per mole versus composition diagram. So that means you can draw 5 free energy versus composition diagram for each temperature, right? As I told, because if you change the temperature, what will happen? What will happen to the stability if you change the temperature? If you change the temperature, what will happen to the stability of a phase? It will remain same, or it may change.
Change.
It will change. That is why we are drawing free energy versus composition diagram, right? Here temperature is different, right? We, for each temperature, sorry, we fix the temperature for a particular fixed temperature. We are drawing free energy versus composition diagram. Just have a look. So first temperature is T1. Just have a look. This is the temperature. So at this temperature T1, if you want to draw G versus X plot, then you have to look into the stability of all phases. So at this temperature, which one is the stable phase? Tell me quickly.
Liquid.
Liquid phase is there. Very good. That means liquid is only stable phase at this temperature T1. What about alpha? Alpha is unstable at this temperature. And what about mixture of phase liquid and alpha? It is also unstable. Basically, liquid is the only stable phase available here. So if you want to draw the phase diagram, this will be like this. So that means, okay, and the question I have, listen it carefully. So if you want to show alpha curve, free energy versus composition for alpha curve and for liquid, so which one will be above, which one will be below? Let me repeat the question. You want to show alpha, G alpha and G liquid in G versus X curve. So which one will be above, which one will be below at T1?
So liquid one below होगा.
Very good. Liquid one will be below and alpha will be above. Why? Because at this temperature, liquid is a stable phase. So obviously the free energy of the liquid phase will be minimum at T1, but alpha will be maximum, right? Very good. Just have a look. This is the image. The first image. This is the free energy G versus X. X means here XB I have taken because this is pure component A, pure component B, and this is the composition of XB, right? You can see this is Z alpha and this is the G liquid. So free energy of liquid will be less compared to free energy of the alpha, because at that temperature of T1, you have seen liquid is the stable phase. So you have to remember the phase which is stable have lower free energy, right? Or the position of the phase having lower free energy will be at the lower position. Or free energy curve for a phase which is stable having lower position, and the free energy curve which is having a if a phase have higher free energy, the curve will be above, right? Or which is unstable will be above, right? So this is the situation. So next is the temperature. Okay, next temperature is TMA. TMA is the melting point of pure B, melting point of the pure B, and this line is like this. Just have a look. So can you tell me which phase is stable here? But composition is important. Just composition is changing. That is important also. Composition is changing from 100% A to 0% A in this direction. Or in this direction from B to A is 100% B to 0% B, right? And this the temperature chosen is TMB, melting point of pure B. So which phase is stable? Can you tell me? Like at T1, liquid is the stable phase, but alpha is the unstable phase. Similarly, at TMB, which one is stable?
Liquid.
Okay, fine, liquid. But carefully look at this. This line is intersecting at this point at the end. This particular temperature line axis is intersecting the pure B at this point. What it means? So it simply means at this point, alpha will be there and liquid will be there. You understood my point? At
Yes,
this
sir.
point, alpha and liquid both will be there, right? But if you go from B to A, just have a look from B to A. If you go from B to A, then what is happening? Liquid is stable phase, right? Or you can say from A towards B, initially liquid is a stable phase, but at the intersection point, both are stable, right? So that means if you draw a free energy versus composition plot for this alpha and liquid, how you can show? You can show that from starting from A to B, liquid will be having lower free energy, alpha will be having higher free energy. You understood my point? But when you reach to the point B, they will intersect. Just have a look. This is the plot, right? So free energy of liquid is lower. It is going like this. And free energy of alpha is initially higher. And it is intersecting at this point. So this point is showing you the TMB, right? And if you go from right to left, then obviously that means liquid has lower free energy, but liquid is the stable phase. It is okay up to this?
सर और एक बार समझा दीजिए ना.
Okay, fine. This temperature axis, TMB, this temperature axis, just carefully look. This temperature axis is intersecting only at point P or end B, right? At P or end B, just look at the line. The liquidus line and solidus line are intersecting at this point, right? So when the solidus line and liquidus line are intersecting at this point, that is the only a constant melting point, you can say, right? That means alpha is there and liquid is both are stable at this point. Okay. Only at this point, alpha and liquid both are stable, right? But if you go from this end to pure end A, then liquid will be stable. Okay. But alpha is not stable. But at this point only, liquid and alpha both will be stable because liquidus line, solidus line are intersecting at this point. This is a constant point, right? Because this is the melting point of pure B. You understood my point? Yes or no?
Yes, sir.
So that's why if you want to draw free energy versus composition curve, the curve will be like this. That means you start from, suppose you start from this end to this end. So at this end, which one is stable? Liquid is stable, right? You are going like this. At this point also liquid is stable. At this point liquid is stable. At this point liquid is stable. Up to point B, just before point B, liquid is the stable phase. That means the free energy versus composition curve for liquid will be lower and alpha will be higher. You understood up to this?
Yes, sir.
But at the point B, when you reach exactly at point B, the alpha curve and liquid curve will intersect because they have free energy. Same free energy. You understood? This point.
Yes, sir.
You can see alpha curve and liquid curve are intersecting only at point B. That means at this point, both phases are stable, alpha and liquid. Stable, both have same free energy, right? But if you go from B to A, you can see liquid have lower free energy, alpha have higher free energy. Why? Because liquid is a stable phase. In other compositions, just have a look. Because apart from this end, other composition is liquid is stable phase. Next, we'll move to temperature T2. This is the temperature. This is very interesting because you can see if you want to go from B end to A end, then you can see initially which phase is stable? From this pure B to this point? Alpha, very good. But the moment you reach at this point to this point, which one is stable? Both liquid and alpha is stable, right? But when you come to this point and you are going towards A, which one is stable phase?
Liquid.
Liquid, very good. So that means at different composition, in one composition you have alpha phase stability, then mixture of alpha and liquid phase stable, then towards end of A, it is liquid is stable, right? So this curve will be interesting, obviously, how it can be drawn. So how you can draw? You suppose you start with this end. So at this end, liquid is a stable phase. So you draw a curve where you are showing liquid have minimum free energy, but alpha have higher free energy. Okay. And similarly, go to this end. You can show liquid have lower free energy. So liquid is stable phase means, alpha is stable phase means alpha have lower free energy at this end and liquid have higher free energy at this end. And they will intersect at a point. Okay, just have a look. This is the figure, T2. So you can see this is Z liquid curve and this is Z alpha curve. So at this intersection point, it means both liquid and alpha will exist. right? But if you go from this point to left side point towards A, then you can see liquid is a stable phase. So that's why you can see liquid have lower free energy. GL is in the lower position, G alpha is at the higher position. So GL is in the lower position means liquid is the stable phase, alpha is not stable. But after this intersection point, if you go towards B, you can see there is an intersection. The G alpha is lower, but G liquid is higher. G alpha is lower because G alpha is the stable phase after this point towards B. After this point towards B, alpha is having higher free energy. I think you people have understood up to this.
Yes, sir.
Yes, sir.
And what I have told, when there will be an intersection point, then free energy of two phase will be same and composition is fixed. But that composition will stay or it will decompose into new composition. It will decompose into new composition. I told you, right? So what are the new composition? How to determine the new composition of alpha and liquid? You have to draw a tangent. When you draw a tangent, it will intersect the lowest point of alpha and liquid. This is liquid, this is alpha. And you can draw a projection where the intersection happens to the composition axis. This is one projection, this is one projection. So after drawing this, what you can identify? You can identify each phase have a range of stability, composition stability, or stability of each phase has a particular composition range, right? So from this pure end to this much, liquid is stable phase. From this end to this much, alpha is stable phase. And from this end to this end, liquid plus alpha is stable. I think up to this it is clear.
Yes, sir.
Yes,
Okay, very
sir.
good. So now we'll move to the temperature TMA. So can anyone tell me now, TMA is the melting point of pure A, this point. So at this temperature, which one is stable? As this TMA temperature, which phase is stable?
Sir, alpha.
Just look at carefully look at the position.
So
Alpha is only
both
stable.
alpha and liquid.
Okay, alpha is stable up to just before point A, pure A. You are getting my point, because this particular temperature is intersecting this end. Okay, so this end is, at this end both are stable, alpha and liquid. Okay, but from this end to this end only the alpha phase is stable. So that means from pure end B towards A, alpha is the stable phase, but when it intersects this point, both are stable, both liquid and alpha are stable, like at this point I told. Okay, so how to draw it? So that means if you want to draw a free energy versus composition curve, you start from pure B end. So which one will be lower and which one will be higher?
G alpha will be lower.
Very good. G alpha will be lower and G liquid will be higher. But at the end of the point A, what will happen? They will intersect. They will touch. Okay, just have a look. This is the curve, TMA, right? G alpha from B end, if you go towards A end, G alpha is lower position because G alpha is stable. I mean, alpha phase is stable, but liquid phase is unstable. But at pure end B, both are stable, so they will intersect. I think up to this it is clear. Next, I'm choosing a temperature T3. So this is very easy again. Which phase is stable at T3 temperature?
Alpha. Alpha is stable.
Alpha.
Alpha, very good. Only alpha is present, right? There is no intersection. So you can easily draw a G versus X curve. Just opposite to the which curve? First one, this temperature T1. The condition will be just opposite to T1, because you can see in T1, liquid was lower position and alpha was higher position. But in the last temperature, T3, alpha is lower, liquid is higher. I think you people have understood up to this, right?
Yes, sir.
Okay. So the thing which I have explained, I have written over here. So what I have written, temperature here, T1 temperature, TMB, T2, TMA, T3. And I have also mentioned the solubility. You can easily write which, sorry, stability, not solubility, stability of which phase. Okay. So now what are the important points to remember? So you have to remember some important points. The first important point is free energy versus composition curves are inverted parabola. You people have understood up to this? Whenever you are drawing a free energy per mole versus composition curve, they will be basically inverted parabola. From the previous lecture you have seen, right? Very good. So next is position of, yeah, this is already I have told you, position of free energy versus composition curve for each phase tell the relative stability of given at a given temperature. Okay. Stable phase have a lower position in G versus X plot, right? Which I have already shown you. That means suppose you have two solid solution, and the solid solution which is more stable will occupy lower position in the free energy versus composition curve, and the phase which is unstable or relatively less stable, that will occupy the higher position in the G versus X curve. Shall I repeat it, or you people have understood? Okay, again I am saying if you have two solid solution, and in between these two solid solution, the solid solution which is more stable, that will occupy lower position in the G versus X curve, and the phase which is unstable or relatively less stable, that will occupy higher position in the G versus X plot. This is a simple funda you have to remember, right? And the last important point is if there is an intersection between two free energy, which already I have shown you, where alpha, G alpha and G liquid are intersecting, or G alpha, G beta are intersecting, right? If there is an intersection between two free energy versus composition curve, it means two phases are stable in a range of composition. Okay, you people have understood up to this?
Yes.
Yes, sir.
Yes, sir.
So okay, fine. If you people have understood, now tell me how to find out that range of composition. In what range of composition both alpha and liquid or both alpha and beta are stable? How to identify that?
So by drawing a tangent.
Very good. First of all, you have to draw a tangent to two curves. Then next, after drawing a tangent, what can be done? You have to draw projection to composition axis. Okay, like this. Just have a look. This is a tangent intersecting this curve here. This is the tangent intersecting this curve here. You have to draw projection to composition axis, and that will tell you about the range of stability. Okay, or in the previous curve, if you want to see this one, this is the tangent to the two curves, and this is the intersection point of here. This is the intersection point. You draw projection to the composition axis, and that will tell you about the range of stability of these two phases. It is okay? You
Yes,
have any
sir.
doubt up to this?
Yeah.
Okay, fine. I think there is no doubt. Can you please take the screenshot of the class?
Done, sir.
Okay, fine. You people can leave right now, huh?